Hello, welcome to the EC225 Superposition review. So here in this short video I'm just going to show a few more examples of superposition, and we've seen these before. I've done some examples on it before, but let's just do a few more examples just to make sure that we understand it well. So let's take a look at the circuit here. Again, it's a very simple circuit. Let's say we have 3 volts. Six ohms. Two amps. Nine ohms. So let's say that we're interested in the current through the 9 ohm resistor. So again, we'll see that actually there are many ways of doing this. In fact, we can do this by using other methods like source transformation. But let's just use superposition directly. So if we do that, again, because we have 2 independent sources, we're going to see that the result is going to be made up of the response to the 3 volt source alone plus the 2 amp source alone. So what that means is that Ix is the result of Ix with 3 volt source alone and Ix with the 2 amp source alone. So each one of these is a separate problem, which means that we have to separately analyze those. So let's start with the first circuit. So here's the 3 volts. Again, we must redraw. That's the key. So we have 3 volts, 9 ohms, 6 ohms. Here's the Ix we're looking for, and of course the 2 amp is to the right of 9 ohms, but it's open circuited, so there's no current going in that path. 2 amp is simply open circuited. So this is the actual circuit that we have to work with, and Ix is obviously the current going through the 9 ohms. So this is pretty simple because 6 and 9 are in series. So simply by Ohm's law, there's only one current flowing in the circuit, and that current is clockwise, and that current has to be Ix. So even this current is Ix, right? Just realize that. So Ix is going to be equal to 3 volts divided by the sum of the resistors, 6 plus 9 ohms. So that's 3/15 of an amp, or just simply 1/5 of an amp, or 0.2 amps. So this is Ix due to the 3 volt source alone. Okay. Now if we furthermore analyze the circuit with the 2 amp source alone, now the 2 amp is active and then the 3 volt is short circuited, right? So the 3 volt is short circuited. Basically 6 and 9 ohm are in parallel, so I'll draw it this way, right? Draw it this way, because the 3 ohm is just a wire. Sorry, the 3 volt source is just a wire, so 6 ohms and 9 ohms can be drawn this way, where again the current to the 9 ohm is the current that we're really interested in. So now we have this circuit. So now in this case, we see again a clear way of doing this problem. A simplest way of doing this problem is by simply applying current division, right? Because everything is in parallel. So some part of 2 amp must flow to the 9 ohm, and the rest has to flow through the 6 ohm. So by simply applying current division, we can get Ix. So Ix is the ratio that's equal to the other resistor, right? Not the current that's flowing to the 9 ohm resistor, which is Ix, but it's the other resistor, 6 ohm, divided by the sum, that's 6 plus 9 ohms, right? Times the current that's flowing in, which is 2 amps. So this is going to give us 12/15, right? 12/15 amps, or just 4/5 amps, or 0.8 amps. So the result is going to be the sum of these, right? So the Ix, the actual Ix will be Ix due to the 3 volt source alone, which we found in an earlier step, and then this current that we just found, which is Ix due to the the 2 amp source alone. So Ix due to the 2 amp source alone, and when we add these up, of course, we'll get our result. So let me correct that for a second here. Correct this. So we go back here. This is the 2 amp source. So we have basically, we had 1/5 of an amp, and then 4/5 of an amp, and that equals just 1 amp in total. So that's all we have for this one. And again, there are other ways of doing this problem, but superposition would be this way. It's straightforward, and we try to simplify the circuit as much as we can before we apply the analysis. And again, that's what we should keep in mind, that this is a divide and conquer approach. Okay, so let's go and look at another problem. So this problem will have dependent sources. I did one in class, but again, the key with those kinds of problems is that we cannot turn off the dependent source. We can turn off the independent sources. We cannot turn off the dependent sources. So what that means is that in each of the subcircuits that we have, dependent source has to remain in there. So that's a key. Dependent source remains in the circuit. So let's take a look at this problem. So let's say we have a 10 volt source, 2 ohms, 1 ohm, 3 amp current source, and then we have a dependent source. And this dependent source is a dependent voltage source whose value is 2 times the current Ix, where Ix happens to be the current that's flowing through the 2 ohm resistor. So this is our Ix. And our problem in this case is to find Ix. Okay. Again, we have 2 sources, and because we have 2 sources, again, that means that we have to break the problem down into 2. So the Ix total is going to be Ix due to the, for example, 10 volt source alone plus Ix due to the 3 amp current source alone, and the total result will be the superposition sum of these 2. So again, be very meticulous and redraw the circuit with the 10 volt source in there, 3 amp source gone basically. So here's the 10 volt source, 2 ohms. 3 amp is open circuited, so we omit drawing that branch. We just eliminate that branch. Here's the 1 ohm, and here's the source that gives us the voltage of 2 times Ix. And again, a reminder that this is our Ix. In fact, Ix is the current that's flowing in every element here, because this particular subcircuit leaves just one loop, right? So current going from left to right, Ohm's law says that the voltage across the 2 ohm is 2 times Ix, and the voltage across the 1 ohm is 1 times Ix. So if we look at this, we actually have a loop, a single loop, in which we know all the voltages in terms of Ix are either a constant, right? So 10 volts is a constant, everything else is a drop in terms of Ix. So we can write a Kvl equation clockwise, saying sum of the voltage rises equals to the sum of the voltage drops. So if you go around the loop clockwise, like this, you'll see that voltage rise is equal to 10 volts, right? So we 10 volt rise. Everything else is a drop. So we have 2Ix plus 1Ix plus 2Ix. So 10 equals 5Ix, or Ix, again this is Ix due to the 10 volt source, is equal to simply 2 amps, right? And if you look carefully, this portion here is due to the dependent source, and it behaves like a 2 ohm resistor actually, right? So we had put a 2 ohm resistor there, top to bottom, in place of 2Ix, with the current Ix going from top to bottom this way. If we put a 2 ohm resistor there, the equation would not change. So in this particular subcircuit, 2Ix behaves as a simple 2 ohm resistor, but it all comes out in the Kvl equation anyway, so you don't have to really note that necessarily, but it's just something to think about. Okay, so let's now look at the circuit with the 3 amp source alone. So with the 3 amp source alone, we have the following subcircuit. Okay, so we'll have a 2 ohm resistor that I'm going to draw vertically actually this way, with the current going from top to bottom, because the current is flowing again left to right. So when I kind of move it around, kind of slide it down, that's how it looks like. And then I have my 3 amp current source, and I have my 1 ohm resistor, and then I have my dependent source of 2Ix. So again, in this case, again we're trying to figure out Ix. We can notice a number of things. For example, if the current Ix is flowing top to bottom, again it's flowing into this the node where connection point where the 3 amp meets the rest of the circuit. So again, Ix is flowing into that node. So the current flows from top to bottom to top in the 2 ohm resistor. By Ohm's law, there's a voltage drop of 2Ix, right, from bottom to top. So now we notice that since this current is Ix up here, right, and 3 amp is also flowing in, the current that's flowing left to right in the 1 ohm resistor, if you notice this is simply 3 plus Ix. That's the total current that's flowing through the 1 ohm resistor left to right. As a result, there's a voltage drop across the 1 ohm resistor equaling to 1 ohm times 3 plus Ix. So basically the voltage drop across the 1 ohm resistor, right, plus to minus there, is 1 times 3 plus Ix, or just simply 3 plus Ix. Now that again sets up a loop, and if you look at the loop that I'm interested in, actually the loop I'm interested in, this outer loop, clockwise, for example. If you look at that outer loop, everything is in terms of Ix, and everything is, if you get in the direction clockwise, right, if we do Kvl clockwise, for example, sum of the voltage rise is equal to sum of the voltage drops. If we do this, right, you notice that everything in the direction of the of the circuit in clockwise direction, everything is a drop, right? So if you have a drop of 2ix, we have a drop of 3 plus ix, we have a drop of 2ix. So if we write that down as an expression, everything is a drop, so there's 0 rises, everything is a drop. So 2ix is a drop, plus 1 times 3 plus ix is a drop. Again, I'm writing it 1 time, so you see it's 1 ohm times a current, right? So this thing is really a voltage, okay? Plus the 2ix that comes from the dependent voltage source. So this whole thing is the Kvl equation, and if you simplify, you see that 0 equals, we have 2ix plus ix plus 2ix, that's simply 5ix, and then plus 3, right? So this is the expression. So from here we get that ix, that's due to the 3 amp source alone, is simply minus 3/5 of an amp. So again, as a result of superposition, the superposition sum is given by the two results that we found individually, right? So we have 2 amps minus 3/5 amps, and 2 is obviously 10/5 minus 3/5. We get 7/5 amps, which is 1.4 amps, but it's 7/5. We'll just leave it that way. So again, in this case, the difference from the previous case is that again we had two sources, and they were still we still broke it down to 2 circuits for 2 independent sources, but because we had a dependent source, the dependent source cannot be turned off, and the dependent source has to be present in both of the subcircuits. And then because of its presence, we have to deal with it, and sometimes it's a simple one-line equation like I had here. Sometimes it involves a little more work. But the point is that the dependent source must be left in the circuit if you have a dependent source in the superposition type problems. Okay. So let's go and do another problem. And again, let's look at a problem where we have a dependent source. So because the independent source, I think you kind of see the point about how to approach these kind of problems. But dependent sources, again, the problems are usually a little more involved. They're not that much more complicated, but again, we just need to concentrate on what exactly we're doing to make sure that we don't miss anything. So here's a problem. Here's a 2 ohm. Here's Vx, independent voltage source of 4 volts, 1 ohm. In series with 2 amps. Now when you see something like this, 1 ohm in series with a 2 amp, I mean that whole branch there can be pretty much replaced by the 2 amp source, because the current through the 1 ohm resistor is already established as 2 amps. There's no question about it. Bottom to top, that current is 2 amps, and you see that that 1 ohm resistor won't come into the picture. Okay, so here's our circuit. The top resistor is 3 ohms here, and what we'll be interested in is this current here flowing through the 3 ohm. Let's call that I. Okay, so we're interested in I. Again, we have 2 independent sources, so I will have 2 components. There will be an I that's due to the 4 volt source alone with the 2 amp current source open circuited, plus I due to the 2 amp current source alone with the 4 volt voltage source short circuited. So by superposition we have this sum again. Okay, again 5Vx, that voltage source, remember, that stays. So remember not to turn that off And for example, not to write I as a combination of three factors where 5Vx is one of the factors. We cannot do that because we cannot turn off 5Vx, for example, right? There's no way to turn off 5Vx unless Vx was 0. If Vx was indeed 0, then 5Vx would be 0, and the 5Vx voltage source, the dependent voltage source, could be replaced by a short circuit. But in general, that's not true. Okay, in this case, it's not true, and you will see this. Okay, so again, the first sub-circuit with the 4-volt source alone in there, okay, will be the following. We'll have our 2 ohm. Here's our Vx. Here's our 4 volts. And again, here's the 1 ohm, but the current source is open, right? So this is really open circuited, and so 1 ohm has no current going through it. We can basically neglect that whole branch there. We assume that it's not even there because it's not doing anything. It is not carrying any current. There's no voltage drop across the 1 ohm. So there's really nothing to do there, and I can simply ignore that, right? So as far as I'm concerned, this is a 1-loop circuit. So basically, the 1 ohm over here, simply ignore. Okay. So again, the current that we're looking for is this one. This is our current Ix. Okay. Now, again, you can do this by formal ways. You can use node analysis. You can use all these techniques. But let's try what we can by what we know, right? Like, for example, the voltage across the 2 ohm resistor is Vx, and it's already marked. Therefore, the current that's flowing top to bottom is Vx over 2. And if that's true, then the current flowing through the entire circuit is Vx over 2. So, for example, this current is Vx over 2, right? And by the way, so is this current. That current is Vx over 2. And if I know that current, then I know there's a voltage drop across the resistor, again, as a function of Vx, of 3 ohms times Vx over 2, or simply 3/2 Vx. Now notice something from here that, again, Vx over 2 and I are equal and opposite, right? So basically, I, the current that we're looking for, is equal to negative of Vx over 2. So if I find Vx, I have found I. And actually, I can find Vx in a very similar way to the way we found in the previous 2 problems. We noticed that in the outer loop, right? In fact, there's only 1 loop because the middle 1 ohm branch is actually not there's no current through it. If you look at the outside loop, I actually know every voltage either as a function of Vx or a constant, right? So if I start at the bottom here, for example, if I go up by Vx to the 2 ohm resistor, again, I'm going clockwise, okay? So I'm basically thinking about it this way. KVL, clockwise, sum of the voltage rises equals to sum of the voltage drops, right? So if I start at this point X, if I go up by Vx to the 2 ohm because it's marked as Vx. Then as I go from left to right of the 4 ohm, I go down by 4 volts. And then as I go through the 3 ohm, I go up by 3/2 Vx. And then I go down by 5 Vx, right? So what are the rises? Well, I had a rise of Vx and I had a rise of 3/2 Vx, right? And the drops were due to the 4-volt source and then the 5 Vx source, right? So this is the expression that I get if I do sum of the voltage rises with sum of the voltage drops, right? So what does that give me? Well, I have on the left side, I have 3/2 Vx plus Vx. That gives me 5/2 Vx. And the right side I have 4 volts plus 5 Vx. So then if I subtract 5 Vx from both sides, again 5/2 is 2.5, right? So I'll have minus 5/2 Vx, right? equals to 4 volts, or I'll get that Vx equals let's see, so I'll get 8. Did I do something wrong here? No. So Vx is minus 8/5, right? So minus 8/5 of a volt. You can check the numbers, but I think this should be correct. Looks correct. Anyway, that's Vx, right? So then I, remember I is what we're really looking for. It's the expression given up here. So I, that's the I that's due to the 4 volt source alone, in fact, it's equal to minus Vx over 2, right? Which is equal to, again, minus 1/2 times minus 8/5. So you get 4/5 amps out of this, right? So this is the current that we calculate due to the 4 volt source alone. Again, you can see that it was a little more complicated, not too much more complicated, still the same, you could say, same style. Okay, same style calculation. Now we'll have to put the 2 amp source back in and then do the calculation again, trying to calculate I. Okay, so let me draw that subcircuit. Okay, so that subcircuit looks like this, right? So we have the 2 ohm resistor with the voltage Vx across it. We have a 1 ohm resistor, and we have our 2 amp current source. Again, the point is this current coming in is 2 amps. So it's as if the 1 ohm is kind of transparent there in a way, right? Because just because it's in series doesn't mean the current will change as the current flows bottom to top to the 1 ohm. The current that's coming to this junction point is still 2 amps. Okay, rest of the circuit, there's the 3 ohms. This is the current I that we're looking for, right? And then we have this voltage source 5Vx. This is our setup. Again, it's not that complicated. Again, there's a number of ways you can do it, but again, let's just start with doing stuff that's relatively simple. Again, this 2 ohm resistor that's on the left, the current top to bottom through it has to be Vx over 2. Again, Vx is already marked for us. That's the dependent variable. So the current top to bottom by ohm's law has to be Vx over 2. So that Vx over 2 is also over here. So we have a relationship between Vx and I, right? So if you look at that junction right here, that junction, 2 amp is flowing in. Sorry, this should be Vx over 2. Vx over 2 is flowing out, and also I is flowing out. So because of that, we can write down the following Kcl equation, right? So we can easily say that 2 equals Vx over 2 plus I, right? Or we can say that, again, I is equal to 2 minus Vx over 2. Again, if we find Vx, we have found I, right? So again, we can do that pretty easily because we notice that again, if you look at the outer loop, I know the voltage across the 2 ohm, it's simply Vx, it's marked as is. I know the voltage across the 5Vx voltage source, it's 5Vx. The voltage across the 3 ohm, what's that? It's 3 times I, or if I use my expression from here, right, I can, I can just substitute in, right? So basically, the voltage across the 3 ohm resistor is, right, is going to be 3 times I. Now, there's another way of doing it. There's another way of thinking about it. Another way of thinking about it is the fact that if you actually go around the outside loop, if you have a rise of Vx, right? If you have a rise of Vx on the 2 ohm resistor, top to bottom, then you got to have a rise of 4 Vx across the 3 ohm going from left to right. So we can do it that way too. It depends on how you want to approach it. But for now, let's just write down that this voltage drop is simply 3 times I. And we can substitute in for I, or we can substitute in for Vx. It doesn't really matter. But let's just write down the Kvl equation. Again, I'm going to write the Kvl equation exactly the same way. Kvl clockwise, sum of the voltage rises is equal to the sum of the voltage drops. So again, I'm going in the outer loop in the clockwise direction. So then, again, Vx is a rise, 3I is a drop, 5Vx is a drop, right? So that means that you get that Vx is equal to, again, if I just work it here, Vx is equal to 3I plus 5Vx. Let's just solve for Vx. It might be just simpler to do that. You can also substitute in for I. It doesn't really matter. Or substitute for, you can solve for either Vx or I. Let me just substitute in this from up here expression, the I expression up here. If I substitute in 2 minus Vx over 2 plus 5Vx, I have an equation that just involves Vx, right? So I have on this side here, I have Vx on the left side. I have 6, and I have minus 3 halves Vx plus 5Vx, right? Okay, so let's just work through this. Move all the Vx on one side. So I have Vx is equal to 6. Again, I have 5Vx, and I have 3 halves minus 3 halves Vx. So 5Vx is the same as, again, 10 halves Vx. So that gives me plus 7 halves Vx. And if I just move things around, I'll have minus 6 is equal to 5 halves Vx on the right side. And from here, we see that Vx is equal to minus 12 fifths volts, right? And again, I is equal to 2 minus Vx over 2. So it's 2 minus 1/2 of 12 fifths, right? So it's equal to, sorry, this is let me make a correction there. It was okay, so it's minus 1/2 times minus 12 fifths, right? So you have 2 plus 6 fifths, so that's 2, which is 10 fifths, plus 6 fifths, which is 16 fifths amps. Again, we could have, instead of using I, we could have used V. Again, instead of I plugged in Vx, but I could have gone back and, maybe from like one of these expressions up here, solve for Vx in terms of I and plug that in, plug that in for Vx, and then I just solve for I directly. Anyway, I did it this way. It just turned out this way. So here's the I, and again, this is the I that's due to the 2 amp current source on this value, and from above we calculated also I due to the 4 volt source on, which was 4 fifths. So the final result is that I is equal to 4 fifths amps plus 16 fifths amps. That's 20 fifths amps, which is equal to 4 amps. So this is the final result. of calculating this via superposition. So again, the point of all this is to be able to calculate things by taking one independent source at a time. So again, you have to remember that. You have to take one independent current source at a time. That is the key with superposition. So I ask you to go and do more examples and look at the problems which will be assigned from this chapter. But I hope this video is useful. This is the first time I'm doing a video like this. It's a little bit interesting to sit and talk to oneself, I guess. So I hope you enjoy it. I hope you go over it. If there are any errors, please let me know. But for now, I'll leave it with this. And then next video will probably take on source transformation. How to use source transformation. In fact, in superposition problems, we can use source transformation. So we'll see all about that. But until next time, I'll stop right here. Again, we'll see you next time.